Okay. Thank you very much. Thank you. So, I'm Alessandro Giuseppe Daloia from Sapienza University of Rome, and this work has been done mainly by our PhD student Mahar together with our collaborator Boodaghian. And this work is part of a industrial-oriented research activity, and is part of industrial-oriented research activity that in particular that finance this topic. Basically, here the outline, we start from an introduction, a system overview, experimental setup, signal processing, and finally we obtain results and we will draw the conclusions and we will analyze future work. Basically, we started from the fact that, thank you, that as everybody knows, global healthcare expenses are increasing to aging population, and 1/6 will be basically more than 60 years old aged, and the growing prevalence of chronic diseases. Hence, there is the need of cost-effective, accessible healthcare solutions, able to continuous monitor wearable sensors in order to offer early detection and the long-term management of health problems, and to integrate such sensors together with wearable wireless electronics. Basically, we wanted to improve multi-sensor data fusion to compensate also sensor failure or noise using a complementary information, and to enable more comprehensive data collection than a single sensor setups. Here, the scope of this work is it possible to have this window wider?
Sorry?
I don't see the slide.
Ah, if they were here. Because you have to face me.
Not sure. Basically, the scope of this work is the integration of temperature and force pressure sensing into a wearable to shorten. That's why we designed an analog front-end circuit and integrated inside an tiny 85 microcontroller for low-power signal acquisition and processing, including, of course, analog to digital conversion of sensor outputs. Here, the system overview. In this study, we use the commercial force-sensitive resistor, here shown, and the commercial grid-type thermocouple, both connected to a platform based on a tiny microcontroller. This platform has been entirely designed by our PhD student, and this platform is acquiring analog data locally processed and wirelessly transmitted to an external mobile device using a Bluetooth module, enabling real-time visualization and data logging. Basically, here we have the scheme, and we can see the operations done by the printed circuit board. As you can see, the printed circuit board is very little. It has a dimension of 2 cm times 2 cm, and it enables the acquisition of raw signal via a microcontroller. The image at the right side is, of course, an enlargement. This system has been inserted inside the commercial T-shirt in order to perform some experimental testing. And the A85 microcontroller is programming via the Arduino, and we can see that the embedded firmware continuously sample sensor data and transmit it via a Bluetooth module, and raw data were logged with a party for post-processing. I point out that of course that will be developed. Here it has not been developed since it will be implemented in already existing app. And The raw temperature values are obtained, as all of us know, from measuring the output voltage from the thermocouple and considering the internal reference point, of course, the calibration coefficient from the temperature set. Of course, the data are really affected by noise, hence a moving average filter is applied to stabilize and smooth the temperature data. Following with, of course, the well-known law of the moving average filter. Here you can see the first result. I point out that the T-shot, of course, before it was not wearable by the user, by me. And later, when I wear the T-shirt, of course, the temperature was set at 36 degrees. You can see clearly the effect, the raw data and the filter at the measurement, and it clearly detects the body temperature. And concerning the data applied by the force sensitive resistor, we applied the continuous wavelength transform to provide better time frequency localization, and then it is performed by converting the per-filter signal with scaled and shifted version of the method wavelength, resulting in a decayed time frequency respiration of the signal, as you can see. The spectral characteristic over time is derived from the raw measurement and are obtained by the battery flow filter. This enabled the time frequency analysis and the fatigue improved interpretation of the dynamic behavior of the measured signal. Then we can see that the effect of continuous wavelength transform frequency depends on the selection of the peak detection, and of course we can see the differences applied the 110 Hz range with respect to the 15 Hz 30 Hz band amplitude. And we can see that the respiratory components reduces the variability by suppressing low modulation frequency in the first phase, and at the other end, in the second case, fluctuations appear affecting the detection and consistency. These signals are obtained using a Gaussian kernel to achieve smooth behavior, and the peak detection becomes, as we can see, more stable and reliable. In particular, we can see that the red process marks the detected peak, and the dashed line indicates the purity alphas. As a conclusion, a multimodal sensing system, it has been developed for continuous monitoring of body temperature and respiration. This system has been tested employing a commercial K thermocouple and the force selective resistor integrated with the signal processing environment. And we use a simple moving average and butterfly filters to reduce noise and stabilize signal. And we extracted the time frequency filters via wavelength transfer, and it is being validated. It is simple for clear participants. It is quite important to notice that the dimension of the fact that it is a very low power consumption. Then this filter has been applied not only for, of course, the future work concerned to expand and to improve it, but I want to point out that this method has been successfully applied also for non-commercial thermocouples, such as the one recently developed with graphene-based PVDF sensors that here reported, and you can find also here the reference of the innovative thermocouple. Hence, this system can be applied also for unconventional or uncommercial thermocouple. Of course, that will be under study. I like the flexibility of this system. Thank you for all. If you have any questions.
Thank you.